structure here and going for Aristotelian dictum, whatever possesses dimensionality's body. And Cartesius, he said, length, width, and depth simply is body, or our body, whatever. And Sophie's thesis, which is in the bottom of much of elementary particle physics, dealt with straight lines of length equal to 0. I think that's a nice formulation of what could be a point, but could also be a partial derivative. Anyhow, that's what Sophie's is about. And Schrödinger started this Wellenpaket idea when he actually combined light in a box, as it combined the space and you could say the matrix or the wave function in one and the same hybrid. And this brings to loop quantum gravity that we have not only to formulate the string but also the stage where the string acts, and also to make them one and the same thing. Yeah. So that's a kind of theoretical or practical, state start. And this is what Lee truly does. And he's not, he's not pronouncing it lie, he's pronouncing it Lee. Anyhow, it's Norwegian. And what he did was that he transformed the straight space, Plücker, as it was called in those days, 1871, by a polygon projection to the spheres, rectilinear geometries, which you today call infinitesimal generators. So it's a kind of transaction between straight and straight, but bringing into a new kind of geometry. And that was his first work, and he actually founded spherical geometry. Not many know that, but that's a fact. Anyhow, I translated his thesis over den klassiska geometriska transformationen. And of course the English would be over the class of geometrical transformation, but it's accessible now online, so I would perhaps recommend to just check it out and read it, because it's in a way transforms also the way you look upon Lee. What did he actually do? What did he actually say? It's often very good to go back to the sources. That's my practice in medicine, because I'm a medical doctor, I should say. And I should also say that this work here is not of mine alone, but I'm co-working with a Nigerian group, Alexander Animalo, and that's part of their cosmography is included in the thinking here, because they have an old, very ancient remnant of some very original cosmography that's called the cube hexagon thing, and it's also very practical, as primordial things used to be. Anyhow, what is he doing? Well, you could say he's transforming between round and cubic. That's the general idea. But perhaps he's more like transforming between straight and round, not the other way around. Because Leonardo da Vinci and other has been to inscribe the cube within the sphere, but I think what Lee does is that he inscribes the sphere inside the cube. And that is a much more constructive kind of. So you could say that this idea, of course, of a transformation or transition between straight and round is very old. You have it in the Vedas, but you have it also in the Nordic mythology. The kind of meeting between the ice called Niflheim and the warm kind of Muspelheim. And the idea that everything is generated in that kind of meeting. This has been absolutely transformed. This is not. Could I feed my stick again, because I get another kind of. This is not to the.
Do you need help or you can do it yourself?
Yes, I think if I can manage to get the stick in, because I got it in the... So here is my stick.
I have a stick, you like.
Oh.
To bond.
I have to finish this first, I think. Sorry, because it comes in a totally blurred kind of order.
And you like also to
Yes. Now it comes right. I have to go back.
Okay, if it's in the... wait, is this the correct order here?
Yeah, I think...
Okay, then we keep it like this. We have the side ones on, a bit easier than...
Yes. But we have to go back to the start. Is there some way of going back to the start of it?
Just scroll.
I'm just... I couldn't see it.
Yeah. Scroll it up.
Drag that.
Drag that. Yeah.
then click.
Once again.
A bit more. Yeah.
Just wait a second because it's
Thinking about
it's thinking about it. It does.
Even for...
It's a slow computer. That's all.
Oh, it's starting again, but anyhow, this could be a big repetition. Then I can do it much faster. But it's the kind of... No, I'm on the meaning of life, yeah.
You like to put it in?
No, I think I can deal with this.
Otherwise,
Yes.
You like?
Okay.
You have it here.
Oh, yes.
So nothing.
Yes. Yes. No, I think I go by this. Yes. Thank you.
Niet alleen als een meeting waar
Yes.
Well, anyhow, this was a little repetition, you could say, in advance, but anyhow, it's obvious that this transformation between the, so to say, sphere and the cube can't be done in one big bang. So it has to be done very stepwisely, and to that end, we have the algorithms and geometries, and there are some killing loop vector diagrams that describe the commutation relations of these algorithms. And nowadays, the killing diagrams are actually used as they are, as a kind of crystallographic structure. And the A2 diagram, that is the plane diagram of SU3, but it's over the complex numbers. And one thing is how to duplicate it. And one way of duplicating it to get it over the real numbers and make it three-dimensional is to incline them about 60 degrees against each other, and you get a kind of combined structure here, which is the A2 diagram inscribed within the sphere. And the nice thing about this is suddenly it's not only over the plane, but it creates a network. And that network forms a lattice that is continuous. So you can say that what we are dealing with here is the phase transition between the inner surface of maximal extended Euclidean Pleckery space and the outer surface of the maximal contracted sphere. So what happens is not happening in the sphere, but it's happened in the transition between a maximally extended and a maximally contracted geometry. And the Lie groups are governing this, but as applied to the elementary particle structures of the standard model, they used to describe rotations of the, so to say, thought of particular components, quarks, that were within this thing. But in fact, Lie himself said that these are general translations and could also be applied to semblability, transformation, translation, semblance. It's a kind of general kind of transformation of straight to a curved symmetry. So this is one way of doing it perhaps, and you have a lot of things you could do by this, but more specifically, what's happening here is, again, the transition between a flat and a curved surface. And this is one way of describing it, is infinitesimal kind of steps taken. And since we have a little thing here which consists of steps, unit vectors. We also see that the kind of projections here with the square root of 2 and the square root of 3 form major semi-axis, so ellipsoid transformation of this sphere here, but that's another story. And I have been working with Peter since 40 years soon, I think, about this, and still not reached conclusion. But anyhow, well, we go on with this. So we say that we have transformed by this network the cube into another complex, which is the only other Pythagorean solid that is, so to say, space-filling. And that is the well-known combination between one octahedron and 2 tetrahedron. But the funny thing is that now it's continuous. So you can make this wandering, as it were, over the root vector lattices, which you can't do in a cube because you collide. But now suddenly you have something that could be continued. And it has the same measure as a cube. And in fact, it's the dual of the cube. So, in a way, we have transformed here, and I should test this now, yes. So we have the IVM unit module here. This is the wave, and it creates a lattice. And this lattice has the form of one octahedron, 2 tetrahedrons. And it has also the structure of what we call an isotropic vector matrix, which is, of course, a very fundamental structure here. And my idea is that actually if you globalize this kind of root vector combination, you get into a space-filling structure, because the IBM is a space-filling thing by itself. It's one possible geodesics here where you can connect this, and this forms a truncated octahedron. And the interesting thing is here how the shelving of the octahedron is, and it goes absolutely to the shell formation of atomic structure. I mean, K, L, M, N, O, P, Q, R, S, and it's what we call a palindromic Bohr orbital kind, which goes very much to the shells of the atom. So, because the P shell, for instance, is filled by 32, and then it goes to the Q, and that's filled by 18, and so forth and so on. And this very nicely repeats that, and if you compare then the inertia of this rapidly thing, which has a big length, with the kind of unit steps it takes here, you see it comes out there and takes an extra step, we get the proton-electron mass ratio very nicely. But another way of doing this is accepting that we have formed what we then call a wave packet. That is again the kind of the wave caught within a box. And the box and the wave, they are created themselves. And if we connect them like this, we do skip the problem of connecting these rather intricate helicoid structure. We just pack the boxes and see how can we pack a box space-fillingly, knowing that it's going to bear, as it were, the interior by their combination. And I came to this idea that the best thing would be a trapezoid kind of combination.
Why do you call it palindromic?
But because it's 2, 8, 4, and then it's the same in the end. And,
okay.
Yeah, so it's you can see it from either plane. Anyhow, you could do a lot of things by this little trapezoid toy model, you could say. But the interesting thing is perhaps if you combine these toy models with each other, they again repeat the structure. So the rhomboid here is forming a new rhomboid. And interestingly enough, in that kind of composition, it also is a central hole. So there is actually a central hole that translates the whole structure a bit. I'll come back to this. And you could make a tessellation of it. And this tessellation is, of course, the self-combination of this. But you see it contains holes. So it's not complete, it lacks something. And that is why we have to have a complement But it is actually the kind of things that characterizes crystallization processes at very, very small scales, younger. So we have these diagonals. One thing that we tend to forget in crystallization is that it's not only flatness or dilatation, as you could call it, but the dilatation presumes some kind of thickness also. So what is happening between the vertical, and that is why we need to have this vertical kind of stashing. Just very briefly. So what is happening then? Well, we have the idea that we have the bottom plate here, and it's of course extracted, as it were, from the cubic space. So what does it leave? It leaves a remnant. It leaves this cap that is the, so to say, consummation of the kind of, you know, cubical part of space it's extracted from. So it's really a kind of rope trick, Indian rope trick. It generates itself by generating itself, as it were, but it gets a two-component structure, which creates itself. And then suddenly, this cap provides the extra meridian corners here. So you have a space-filling kind of tessellation. So this fills space completely by repeating its own pattern. But it's a problem here, and I'll come back to that. But I must show that we have an analog here in the ribosome translation apparatus of protein information. It is not enough with the bottom plate. You need to have a kind of cap also that is subjecting the transformation to its, yes, I think I'll keep time here. So we go back here again, and we see there is a problem. In order to reach 153, there has to be 5 extra spaces, 5 extra steps, and we can't really accommodate them here. So we have to look at another structure, perhaps, that allows this extra step. But again, we can have use of this. For instance, Einstein-Bose condensates. They are suddenly, so to say, halting altogether and don't have any. So we can assume that this could be a crystallization form that could exist in certain areas of material composition. So I made a little toy model of this. So I made this little bottom plate, and I took the remnant from the roof, and I combined them to a little module, which is then the compound structure. And this is both. But now you see it is a flat roof also, because the problem with the module is that it has a flat bottom, but it can't be stashed because it has not a flat roof. So therefore, but now we have a module that is flat in all extensions, and we could accordingly combine it as made here. And we see again that the packing comes into 2 configurations, one with central hole, but one without a central hole. And that, I think, is rather fundamental. But still, the problem is that we can't really accommodate the extra step that is needed to, so to say, provide an inertia to the structure. Instead, we would say that the packing of the closed variety itself would just lead to a very fixed and movingless kind of condensate, which you could call the Beck condensate. It could be a kind of crystallization variety, but we have the possibility to find a way out of this by so to say, combining the modules in a linear sequence, and the diagonal string packs the plane, but the weight string does not pack because it gets crowded here, so it overlaps. But we see that we get a kind of structure which has a kind of oblique, and this would then be the proton isobacter, because the proton and the neutrons are coming into the module later. So we have some module here, a little module, and how to, that is on the elementary scale, 10 to minus 15 meters or something like that. How do we increase the width so that it could fill up the atomic size, which is 10,000 times bigger. Well, that is by self-replication. It replicates its own structure, as it were. So that's the general idea, that we could come from the elementary size to the kind of atomic size by just self-similar repetition. And then something happens in this, you could say, harmonic universe that is so balanced, and we could say it's not so balanced after all, because we know this plasma, this primordial plasma, there are self-collisions and a lot of perturbations, and thus enters the nucleogenetic era that squeezes out the kind of collections again from the start and ejects them, in this case, upon a plane to make them. So we can see here that these unit isovectors, they go into, by also they're producing their own reflections in the ejection, so that will become a positron instead of an electron. Anyhow, they fold themselves, so we have here the helium, the hydrogen, and this is the block, but to form the gas, it turns like this. Anyhow, I don't go into details here, because it's a subsequent folding that produces two units, one here and one here. And these are the only two blocks you really need. Again, it's a problem of the extra step. But anyhow, this nucleogenetic era squeezes out these elements, and they are left to combine by the big hammer. And it's of course a very violent process when it happens, and it can only happen in the core of supernovas and whatever. But anyhow, the system here it's being scaled off, as it were, in the kind of layering of the module. So if the two central here, we have helium. If you also take the core 8 here, we have, helium. Yeah, neon, of course. And here, if we take the next 8, we have argon, and then we take the outer shell here that is left, we have crab. So it's a kind of oblique kind of scaling off. And we see that coming to organism, for instance, we haven't reached the whole potential. So we have the potential up here for even more. But I only showed the noble gases here in the kind of dismantling structure, as it were. So operating only with these two, we can build on lithium here, for instance. We could have next here, and we could see it's the systematic addition of these marginal elements, you could say, and giving the kind of also oxidation numbers that we apply. And here I just skip, but it's filling one form which is now, it's got no extra, this is neon of course, and it has got no free positions. So it's a noble gas. But then it starts with sodium, and that has 1, 2, and then it goes on with magnesium, that has 2, and so forth and on. And then the whole thing is just to fill it stepwise till we reach argon, which is again a structure that has no free size. But again, the ground module gets a space filling cap with flat roof enabling vertical packing. We can call it atomosome because nucleosome is already occupied. Anyhow, it has the missing corners and it actually tessellates, but it can't lodge this extra step which is necessary to introduce motion into the system. So therefore, you can make another construction here. You collect, as it were, the same number of elements from the margins of these, because this is, of course, something that is done absolutely not by a cosmical sensor or something. It's just made by the suction of the transformation itself. So if you operate with a structure like this, you find that you come into 152. It's the bottom plate, and they have a good combination, but they have, so they can't really make a tessellation because all corners are filled. But if we give them that extra corner, yes, yeah, if we tessellate them with a hole instead, because which is the other variety, they suddenly tessellate. So that's an interesting observation, you could say. And if we then connect them with an extra step in the bottom, then we have something that really tessellates as a parallel epipede. Because it has to be built on with a cap, and the cap introduces these 6 extra pillars to get 153 themselves. So now we have the ready module. I didn't build a model of it. It's easy to build, but I think time. Anyhow, so hydrogen would be protium. I mean, the one without the neutron would simply be that one with a flat bottom here, and that would tessellate by its mirror image into a kind of structure which has that kind of displacement vector identified as a proton, but it hasn't got a torque, so it's just a static structure. So something has to happen also with this, and this is what happens. A very, very, very simple flip that changes the kind of module's attitude, you could say, characteristics to a more, and this is what I call hydrogen. This is the ready module, and it's got an infinitesimal displacement vector identified as 1 electron because it's a hole here. We don't see the hole now, but we can say that this is now something that has both kind of protonic infinitesimal displacement and a kind of translation here. And that combines very nicely to a kind of structure that is self-tessellating. It cocks in here in the corners, and it's got 2 kind of oblige movements up, and it's got also, you can see here in the next slide, it's got 2 displacement vectors, because the displacement rotation here, which is not actually a rotation because this thing doesn't rotate, because should it rotate it would collide against itself. It's more like a kind of layering of the thing that goes around but doesn't cog in the surrounding. Anyhow, I showed very. So now you can start to use this unit perhaps in a more constructive kind of self-assembly, which I would repeat must also be space filling, because the whole idea is the space fills itself, and thus it can't be any loopholes. If there is loopholes, there will be, of course, a lot of isotope turbulence, of course, and there will be neutrons here and so forth and so on. And all would strive to, so to say, fill out the kind of space so there is no holes in it, because that's absolutely horror vacui there. But anyhow, if you combine those 2 elements, which are the only one element in a way self-generated, which is what we could call the alpha, because it's characteristics of alpha decays, but we could call this the beta, because that's characteristics of the beta things that happens. But the lithium would be that we take the proton here and we connect with an electron, and we suddenly have a structure that would accept 1 electron here as a kind of combination. Beryllium would be 2, of course, and that would be 2. It could also be made of 2 protons, but anyhow, it's a big variation. Boron would be 3, and carbon would be 4, and that's very interesting because now we have this kind of tetra coupling potential, but that could be rearranged also to a 3-fold or whatever. So I just show one example just to give the idea, but it's still space filling. And now from this, because of the diagram's complexity, I also make a kind of schematic representation of the combination properties. So nitrogen would now start to reduce its free binding sites, and oxygen would only have 2 and still be detachable, as it were, space filling, and fluorine would only have one, and be a very, very strong hydrogen receptor, of course. It would actually try all what it can to either combine with itself or get out hydrogen. So this with only one electrons there are. And then coming to neon. And neon, of course, has no free sides. And then one goes on with sodium, then comes one side again, because now the next, so to say, full portion is to be filled. Sodium would have this, and the next one would be magnesium, just one variety of it, and the next would be aluminium. This is one way of performing it, and the next one would be silicon, and that is a whole, because it's got a very big range. I come back to the oxygen sides. Phosphorus would have 3 here, and sulfur would have 2, and chlorine would only have 1 again. It's very strong acceptor, so this is the substrate for hydrochloric acid. We can see it here. Sodium chloride will become sodium chloride, and that will be stashable, also space filling. And argon would again fill the kind of, yeah, I think I have 10 minutes perhaps, hopefully. Yeah. Anyhow.
Much more.
What?
Much more than 10 minutes.
Okay.
20 minutes.
Okay, but anyhow, so we see that the first, you could say, first cycle, you could say, of constituting the atom is filled by a helium-hydrogen center. It's coming to a neon kind of cross structure, and it's being filled by argon. And the next phase is also 18, and the next is 18. So we could imagine to stash on like this, and then continuing this kind of stashing, because we must all the way to 118, which is far, far away here. And how could this hold? Well, we can see that we would be consisting of 18 columns and 7 rows, roughly, and it could be organized. The colors are only assumed, applying to the color of the neon on the noble gases in their oscillation tube. But so the coloring is on that way, but I also think it's good to color to keep the pattern clear. But if we compare with the ordinary particle structure, we see that also that contains 18 columns and 7 rows. But the problem, of course, are the big, that you have to go with the actinides and so forth and so on to introduce them, and you have to also accept empty holes, whereas this one should fill it continuously. Anyhow, it's not going further than this. But things become in a way easier after coming to argon, because then you can just add one beta thing absolutely randomly, because there are so many varieties. But if I show one, the potassium will be like this, and that's of course introducing the next TRELL here, which I give the color of that gas in the element. And that is of course easy to tessellate, space filling, but you can also see that potassium and chlorine nicely fit to potassium chloride, and this potassium chloride is tessellating. And potassium chloride could also be by another variety of potassium, of course, and that would create a square block. So that would be instantly possible to. Calcium would be 2 in this shell, and it could, of course, tessellate. And calcium chloride would also be easy to form, and that would tessellate. And scandium would be 3, and that could have another orientation also, and then it tessellates like this, and it also can make scandium 3 chloride, sitting in the middle here and gripping 2 here and 1 there. So scandium 3 chloride could be easily reproduced. And also the scandium 3 chloride thing tessellates by itself, so it fills space as a compound. Titanium would be this, and tessellates. Chloride, titanium tetrachloride would be easily made because titanium here and then it has 4 free. And it would tessellate. Yes, vanadium, don't know that, but it's vanadium dioxide, for instance, could be formed in this way, often by its mirror image. Chromium is here, and chromium also have various forms. But I stop here a bit. I make a gigantic manganese, really. But I just show that in this form, mangan has, of course, 1, 2, 3, 4, 5, 6 free being side, and it has oxidating states ranging from +6, but going all the way to minus. So, how do we arrange for a minus? Well, we build up alpha things and we put a little defect here. So this would now suddenly be an acceptor, but still having oxidation state -1, but still have the same kind of mass and charge distribution. So it's starting to be, iron, for instance, would have this structure, I think, and cobalt would have this structure in one tessellation. And we are on the mid of a series now, and in the mid of the series, before that series is concluded, it's just a lot of acceptance, but then it's getting narrower and narrower till we have the next noble gas. But I think I just make a little question mark here. How do we go on? Shall we find the kind of things that we have to fill by this, or is it a diagonal? We have so many choices. And shall we go on and find xenon by just filling the next rectangular position that we could conceive of? Or should we just have the stochastic answer? We can be very eclectic here. We can go on with every kind of combination as long as it fills the stipulation of filling space and being able to combine with other of its kin. And I come back there to the actual origination of the idea that you could assume that the acrylates are multiples of hydrogen. So we are only actually making the hydrogen combination here. And we see that the stability stops here. Up here, we only have radioactive. So we can't really expect to find space-filling tessellations, but we can assume a lot of neutron talks and unrest coming in there, trying to solve this before they have to leave into lower states that do have stability. And I think the human being stops about here in combination, well, some extra cobalt perhaps, and material things perhaps what we have use of at least stops here, but here are very exotic states, but they exist, and they exist as a kind of ejection from the plasma. So I would stop here and thank you for your attention. Yes?
So I have 2 questions.
Yes.
One is, I always wondered, when I was taking chemistry, I always wondered why couldn't there be some sort of building up from hydrogen like it was a building block?
Yes.
And you have just shown, well not shown, but you just suggested to me that there is a possibility of that.
Yes.
Because that was a comment on the next 2 questions. So the islands of, you say at the radioactive, what about island? I know nuclear physicists at University of Liverpool are looking for islands of stability at higher.
Yes. Yes.
Is that possible?
Yeah, but I think it's possible, but that will be very, very
Exotic.
short-lived things.
Short, yeah, they say they're
Yes,
very
yes,
short-lived.
yes,
They
yes.
don't. So yeah, so the ones that live the longest are the ones that yeah.
Yes.
Okay.
But anyhow, the idea is that the atom is a kind of cable, and it's got a kind of neuronal structure. It's remarkable how many coincidences there are between, for instance, elementary particle and the human neurons and so forth. It's all, of course, a kind of self. But I think, would that be in conflict with the idea now of nuclear physicists? No, because nuclear physicists have to stash the kind of protons and neutrons inside a kind of globe that is very tricky, and I don't think they have come further than perhaps a couple of atoms to find. But here you also have the kind of reflection surface for the spectrum. Yeah. So you really photon. Yeah.
So that this structure, this building, growing structure.
Yes. Yes.
Does that mean that there's certain? Because I hear about magic numbers. Are there special numbers where these are super stable and building these out of tessellations? Is it more like a real? Is that how we should be looking at these atoms? It's
No, I think just combinatorial.
just combinatorial.
Yes. I think it's
Not an actual spatial
No.
representation.
No. But it's not automatic generation, because we have to realize that only gigantic pressure
Yeah, like
inside supernova can come over iron even, and it takes a lot of energy to get this kind of swarm, to get this kind of letting it combine with itself. But in that case, it's combinatorial. But for instance, calculating the kind of pressure that would be needed, but I think it's a model that is possible to develop. You know,
Yeah.
I think.
Colliding neutron stars as well. Don't they produce a lot of the higher elements?
Yeah.
Colliding neutron stars
Yeah.
produce a lot of the higher elements as
Oh,
well.
yes.
Gold in particular, I've understood.
Sorry?
Gold in particular,
Gold,
I've
yes.
understood.
Yeah, gold is
It is the
iron,
alpha,
yes,
yes.
and mercury, yes. So there are, yes. But well, it's a toy model, but I believe in it.
Yeah.
Yes.
In all your drawing of patterns, do you generate them by an algorithm, or you make yourselves
Yes.
the pattern by hand?
Yes, I made it by hand, but yes.
Because it's possible with cellular automata.
Yes, I can imagine. Yes.
Yes, because I've made many simulations with cellular automata to generate fractals and so on.
Oh, yes.
And I generated very similar pattern as you have.
Oh.
And I'm practically sure that it could be possible to generate all automatically.
Yes, that would be.
Doing as
Yes.
you explained how
Yes.
I could make that.
Yes.
Yeah.
I have not done it, but I have plans. I mean,
Yeah,
yes.
because if I correctly read what you say,
Yes.
you search for a method to create one, but and to create 100 and 1,000 and
Yes.
so on.
Yes.
What do you mean exactly by that? Because it is not simply the repetition of
No.
the same pattern, or
No.
there are
No,
other
that's-
things which happens.
That's another problem here. It's only one atom, but you have swarms of them, of course, and how do they get together and so forth and so on. But it is a kind of, you could say, permutational kind of. So it does take the idea of permutations. How many possible combinations are there? So this is in the reproduction here, I think.
Yeah.
So
It is like the growth of a crystal, yes?
yes, it's a crystallization process. Yes. So that's the idea.
Yeah, but it will be easier by
Yeah. But it's made only by the line.
Yes.
The only element here is the line, and it's the infinitesimal line. And these algebras and groups are also just manipulating lines on the infinitesimal plane. So this is...
Let's thank Eric again.